Thank you for the opportunity to be with you today and share a little bit of the work that we are doing on modeling resilience and using resilience as a quantitative criterion in urban planning. The main motivation for the work that I will be presenting today is coming from this picture. This is a relatively old picture from 1997. That's the period when I lived in the central Canada in the city of Winnipeg, and city that at 1997 experienced the flood of the century. This is a red river, very large river, and flows from United States into Canada. And one small city very close to the border between US and Canada experienced what you see. The whole downtown disappeared in flames because the firefighters were not able to reach the downtown and take care of the fire due to the flood. Situations like this seem to be happening more often. They're becoming more intense. They're becoming much more frequent. And why is this happening? It's happening because we are kind of living through the very dynamic times of globally changing conditions. We are seeing the continuous growth of the population, very rapid land use change, especially urbanization, conversion of the agriculture and forest lands into urban environments. We are seeing the climate change and the consequences that the global warming is having on disasters and changing conditions for all of us. And all these different aspects of the global change are basically making our problems a little bit more complex. They're introducing additional uncertainties, and the solutions that we need to find have to respond to this changing situation. Both hard infrastructure and soft infrastructure are very much affected by these globally changing conditions. When, the hard infrastructure, I mean the pipes and the transmission lines, water, energy, transport, and communications, and so on. And the soft infrastructure, basically adjustments and adaptation of the institutions, societies, and countries, and organizations, even some cultural change in relationship to different changing conditions. So my presentation is about these two pictures. On the left-hand side, you have a representation of the risk map, where different shades of red color are showing the risk from climate change caused flooding in the city of London in Canada, where I live. Different locations are obviously exposed to different kinds of risks, and these maps are kind of representing and showing that. On the right-hand side, you have a different picture. You have a map that's also showing a city, and you have a temporal graph, which is kind of picking up the change of the conditions during the flood event for different locations within the city. Let me tell you a little bit more about them. Risk and risk-based approach is relatively traditional in urban flooding. The broad definition of risk is here, product between the hazard and consequences, and basically combination of the probability of this event, of the hazardous event, and the negative consequences. It can be expressed in various ways. The maps are basically the outcome of this type of analysis, and they can be useful, but they are basically static. They are showing you one single value for one location. This could be useful, like in our maps, you can click and you can find out what is causing this high level of risk. In this case, the wastewater treatment plant, which is relatively close to the river, in the floodplain may be affected by this future climate change caused flooding, and therefore, imposing very high risk for this particular location. We can combine the information, we can generate multiple maps. In this picture, you see the difference between the kind of lower level or a lower bound of climate change impact and the risk posed to the city. On the right-hand side, you see the kind of upper bound, and you can see the appearance of different areas, different levels of risk by simply running various scenarios. We can compare the, let's say, 100-year flood events to 250. We can compare 250 for lower and upper bound. We can compare, the 100 and 250 on both sides. So various combinations of presentations of more or less the same information, and that's basically the risk of flooding at the particular location for the particular hazardous scenario. This is, I think, becoming insufficient. And this is the reason, or that's the reason for changing the paradigm. This is the second picture I want to elaborate a little bit, and let me kind of show you what this particular picture is representing. As you can see on the left-hand side, again, this is the urban area. The picture is showing city of Vancouver and the river going through. And what we are capturing here is basically change of the access to health facilities, hospitals, by the people that can be kind of inundated by the flood. As the flood progresses, more streets are becoming inundated, and the people cannot, for example, access the health services. That can be picked up. I am sorry. That can be picked up in a really this dynamic form. As the flood progresses, more and more streets are inundated, and the risk, or more and more people are having difficulties to access. These different colors here in the map are showing basically at each location how resilient is this particular location. And this graph is picking up the kind of change of this kind of access opportunities for the selected location. So you see now the difference. In the previous set of pictures, I was showing a static representation of risk, where in this case, we are moving into a really new area where the risk, which is renamed here into resilience, is becoming a dynamic variable that is changing in space, in time. So from the static representation and some other issues related to representation or use of the risk management framework, for example, difficulties in assessing the probability of the extreme events, difficulties of integrating together physical, social, economic, and other issues. We are moving, and I am recommending and advocating through this presentation, use of the resilience framework illustrated at the previous slide, which is a dynamic in time and space, and also allows not only assessment of direct, but also inclusion or integration with indirect losses, much broader framework than the simply risk management framework. And let me just elaborate a little bit more. What is the resilience? That particular curve that I was showing on the graph earlier is based on the basically system performance. What the system performance is kind of illustrated here. Let's say this is the beginning of our flood event. Let's say that we are looking the number of kilometers of roads or streets being under the water, and as the event progresses, obviously we will be losing, or more and more streets will be under the water, less and less, kind of ability to move the people. And when the kind of flood starts receding, more and more streets will be available for transport, and system will come back. Obviously, we can influence that. We can, either move people before the flood, or we can introduce some measures to prevent the inundation, and that will all affect the shape of this black curve. So it may become the blue or the red one. However, what is important here is that in kind of risk-based approach, we were focusing on the single number. And here, this graph is giving us a lot of additional information. First, we see this change happening over time during the whole event. We see, for example, how fast we lose performance, the slope of this part of the graph. We see how fast we recover the performance, the slope of this part. We see what is the minimum level of performance, so what is the minimum the number of streets and roads that will be functional during this particular flood event. And that's the concept that we used as a basis to quantify resilience. Simply, if this curve is picking up the performance of the system under the disturbing situation or disturbance like flood, then this white area is representing kind of a loss of performance. And the shaded area represent the remaining performance. And, I came up with a relatively simple way of integrating this area, performing normalization, and basically converting this performance curve into the curve that is on the scale between 0 and 1. And that's exactly what we call resilience. The attractiveness of this transformation is that we can look at various performance indicators, like I pointed out the number of kilometers of roads under the water. We can use the number of beds in the hospitals for people affected by the hazard. We can use the economic damage in dollars or RMBs, and so you can basically analyze the performance in their own units, and then through this simple transformation, bring them all back on the scale 0 to 1, that can be added together and represent the resilience of the whole system. The implementation of this kind of idea is done through kind of integrating simulation and some spatial analysis. The simulation takes care of the kind of key feedback relationships between the resilience or impact and adaptive capacity. And if solving this differential equation through the kind of simulation model, we can come up with this, curves, or sorry, the representation of graphs that are showing the change of the resilience in time. If we perform this kind of analysis in multiple points in space, see the horizontal, see the vertical axis as a time axis, and the horizontal space represented by X and Y, you can imagine that at the particular location, at the particular grid cell, we can create the graph, temporal graph as shown on the previous slide. And connecting all these graphs across the region, you get the map that is basically showing the change of resilience in time and space. That's what I illustrated earlier. Here's one example, just to show you that we did some serious implementation testing of the concept and idea and methodology. We were looking the impacts on Vancouver area, which is the west coast of Canada. Most of you are probably familiar with that, which is exposed under the climate change to sea level rise, riverine flooding. There is a large river, Fraser River, that flows through the city. And we looked into a set of different climate scenarios, about 7 different scenarios and different options to find out the impacts on the city. We considered 4 different impacts: physical, like inundation; social impacts, the number of people being affected; health impacts, the needs for the health facilities to take care of those who are affected by the hazard; and economic impacts, which are measured in the monetary expression of the damage. We utilized all the information in spatial and temporal form. We performed the calculation as I illustrated through that quantification process. And in the end, we were able to generate a very large number of different maps that are kind of showing the Vancouver and showing the resilience level of different regions for different scenarios and for different moments in time. Beside the maps, we also have these different, temporal graphs, which are picking up the change of resilience in time. And utilizing the concept, and now utilizing this measure of resilience, we were able to kind of compare various alternatives, how to adapt, how to respond, see what are the best potential options and how these options measure according to the value of resilience. So this brings me to the kind of product that we have developed. This is a web-based system, which is accessible through the address here and accessible to everyone to test and see possibly how the resilience idea and methodology that I mentioned can be implemented in urban areas for dealing with flooding. The system is developed for using examples of two cities, London, Ontario, where I live. This is a small city, 400,000 people, as well as Toronto, which is a larger urban environment. But the main purpose of this web-based system was to basically illustrate how we can integrate that quantitative resilience into decision-making, assist people who are making decisions to respond to disturbance, in this case, urban flooding, or allow them to plan for the future coming events by, testing different potential adaptation options, response options, and alternatives. So the system is built in this kind of format where on the left-hand side, you have a representation of the area which is being affected, as well as you will see graphical representation of the system performance, as well as resilience. And on the right-hand side is another part of the window where different kind of adaptation options and measures can be implemented and in real time changed by, changing the values of these different sliders. By selecting the measures and changing the intensity of different measures, we are able to automatically go back into the calculation of resilience and show on the left-hand side basically how it's changing. This is to kind of build the background. You need information. The users are first selecting the performance measures that I measure. The performance graph is generated through the simulation. In this particular case, we focused on 4 different performance measures: road length under the water, vulnerable population in a number of people being affected by inundation, infrastructure types being protected, and economic damage. Users also have ability to select the different adaptation options, and we divided the opportunities for adaptation into kind of proactive measures or measures that can be implemented before the disaster, and the reactive measures that can be implemented during the disaster or during the emergency response. Examples of the proactive measures you can see on the screen, like lot level protection measures that are very local around the homes and houses, drainage infrastructure maintenance, like cleaning the infrastructure, allowing water to move faster, adding or twinning the critical infrastructure, and so on, including increasing the redundancy. As a reactive measures, we use the temporary diking, pumping, and other potential ways of measuring or determining how the system, how the city can respond to the flood disaster. When you kind of implement these selected measures here, and then you see these are the selected 3 different adaptation options in a proactive form, we can kind of move the sliders and attach the value to these different measures. On the left-hand side, the system immediately shows the 4 selected system performance, like roads, like damage in material, like number of types of infrastructure. So there are 4 graphs under because we selected 4 different impacts. And for each graph, you will see the kind of in yellowish orange, the performance before any measure being implemented. And blue as immediate response to selected measures and their kind of intensity. When this is done, selecting resilience here on the menu transforms the previous performance graphs into resilience graphs, again, without any measures, and this is without the set of adaptation options provided here. We are also providing ability to kind of read this graph, find out the minimum, find out the values, find out the time. So all the kind of important pieces of information that are coming from this graph. This is a relatively brief walk through the system, and I think very interesting way of illustrating, you know, how the system can, how the concept of resilience can be practically implemented. My message, the final message, is that a risk-based approach has its own value. Traditionally, it's being implemented and it's continuing to be implemented. However, due to the globally changing conditions and the dynamics of the or complexity and uncertainties that are involved with, you know, the current flood management problems, I think change of the paradigm from risk to resilience is necessary. And I think this presentation kind of briefly introduces the concept that has been developed, tested, and implemented. On my website, for those of you who may be interested in more details, there are a lot of publications on the topic. There are technical reports and documents, and also information about the web system that I quickly walk you through. Thank you very much for your time, and I will be very happy to answer some questions.